Welcome to the Deep Dive, where we unpack the most vital insights from a stack of sources, turning complex info into clear, actionable knowledge just for you. Today, we're diving into a realm of artificial intelligence that's, well, fundamentally changing how AI perceives and interacts with our world. Production-grade multimodal AI. For years, AI systems have really excelled in silos, right? Genius at text, stunning with images, brilliant with audio, but rarely able to bring all those senses together. That's changing fast.
That's absolutely right. Our mission here in this deep dive is to explore how AI is evolving beyond that single sense perception. It's learning to process, understand, and synthesize information from multiple senses simultaneously, much like we humans do. And this isn't just, an academic exercise. It's rapidly becoming essential for real-world applications where information is just so rich and varied. We've pulled from a stack of really incredible sources today, covering everything from the core concepts, the evolution of these systems, to practical developer guides and the unique MLOs challenges.
And for you, our listener, this deep dive is about understanding why this isn't just another, cool tech trend. It's about how AI is becoming more robust, more context-aware, and comprehensively intelligent, really moving beyond those limitations of single-sense systems. So yeah, what if AI could truly see the full picture, hear the nuances, and grasp the context all at once? Let's unpack how it's happening.
Okay, so at its core, multimodal AI refers to systems designed to process, understand, and synthesize information from multiple data types or modalities simultaneously.
Mhm.
Think about the whole spectrum: text, images, audio, video, even like sensor data. These systems don't just handle different data formats one after the other. They're built to integrate them into a cohesive whole, sort of like how our brains fuse sight, sound, and touch.
Right. And why is this integration so crucial now? I mean, we've had AI that's great at image recognition or NLP for a while. What was
Yeah.
the big limitation there?
Well, the thing is, the real world is rarely confined to just one sense. A model trained only on text, it just can't understand visual context. And a vision model, well, can't really grasp a narrative without language. Think about when you talk to someone. You're not just hearing words, you're instinctively interpreting their facial expressions, their body language, the whole environment. Single modality AI often misses that entire crucial contextual layer. Multimodal AI, by sort of mimicking this human cognition, lets the system tackle far more intricate problems.
So it's really about reducing ambiguity, making AI more robust. Like if one sense isn't quite cutting it.
Precisely. This fusion dramatically increases resilience, especially when there's noise or missing information, because it leverages the strengths of different data streams. Take a simple text message: your service was great. A traditional text-only sentiment analyzer, it would absolutely flag that as positive, no question. But if a multimodal system also processes the accompanying audio and video, and it picks up, say, a sarcastic tone and an eye roll, then the true sentiment becomes clearly negative. That's the power right there. Each sense offers a piece of the puzzle, reducing the chance of misinterpretation.
That makes total sense. Okay, so if we pull back the curtain a bit, how do these systems actually work under the hood? It sounds incredibly complex, getting all these different senses talking to each other.
It is complex, yeah. But every multimodal AI system, sort of regardless of its specific architecture, fundamentally has to address three really tightly coupled challenges. First, there's representation learning, then cross-modal alignment, and finally, information fusion. These are basically the foundational pillars.
Okay, pillars. Let's start with the first one, representation learning. This sounds like it's about making sure all those different inputs, pixels, waveforms, whatever, can actually be understood by the machine, forging a common language.
Exactly. The challenge is transforming fundamentally dissimilar data into a format a machine can not only understand but also compare. Raw data types are just so different, heterogeneous. So to make them usable, each one needs to be converted into these dense numerical vector representations, often called embeddings, that capture their semantic essence.
And how do we actually do that? Does a picture literally become a number and a sentence becomes a number too? Is that the idea?
That's where specialized unimodal encoders come in. So for images, we use powerful vision models, like based on convolutional neural networks or, more recently, vision transformers. They excel at breaking down pixels into meaningful features. For text, you have models like BERT, which are known for understanding language nuances and context. And for audio, systems like Wave2Vec2 are designed to pick out patterns in sound waves, converting speech into numerical representations. Each of these converts its specific language into a powerful numerical fingerprint, essentially, and the ultimate goal: project these different fingerprints into a shared or common embedding space. The magic here really is that in this space, semantic similarity literally corresponds to geometric distance. So the numerical fingerprint for an image of a cat should be very close geometrically to the fingerprint for the text, a photo of a cat.
Okay, so the key is this universal translation, effectively. But
Hmm.
if a picture becomes a number and a sentence becomes a number, is there a risk that some subtle meaning gets lost? Or how do we know they're really saying the same thing to the AI?
That's a great question, and it leads us right into the second pillar, cross-modal alignment. Or, as you put it, connecting the dots. It's not enough just to know an image and its caption are generally related. You need to understand which specific pixels in the image correspond to which specific words in the caption. Or, which part of an audio clip relates to a visual action. This is where the AI learns to identify those really fine-grained connections.
And historically, how is that done? I imagine it being pretty painstaking.
You're right. Historically, it often involved expensive explicit alignment, meaning like manual human linking, literally drawing boxes around things in pictures and labeling them over and over. Very labor intensive. But the field has really shifted decisively towards implicit alignment. Here, models learn these connections automatically from just large-scale raw data pairs, think images, and their alt text scraped from the web. The dominant technique for this, contrastive learning. Models like OpenAI's CLIP, for instance, learn by being shown millions and millions of image-text pairs. The models that optimize to maximize the similarity between the correct pairs, say an image of a cat and a photo of a cat, while minimizing similarity for incorrect pairings. This implicitly aligns the semantic concepts without needing any explicit human annotation of like image regions.
Right. And I've heard about cross-attention and transformers being a big deal here, too. Does that play into this alignment piece?
Absolutely. Cross-attention layers are a more advanced mechanism. You often find them in transformer architectures. They allow tokens from one modality, say text, to dynamically weigh the importance of different parts of another modality, like specific regions in an image. This means a text description can literally attend to the relevant visual regions, learning these highly granular, context-dependent relationships without explicit instructions. It's kind of like the AI's internal spotlight, shining on the most relevant bits of the other sense.
Okay, so we've given AI this common language for its senses, and we've helped it connect the dots between them on a granular level. The final piece, then, is this science of synthesis information fusion. How do you actually combine all that rich sensory info to come up with a single intelligent answer or action?
Exactly. And the choice of fusion strategy. It profoundly impacts the model's performance and complexity. It determines when and how information from the different senses interacts within the network. There are sort of three main approaches, each with its own trade-offs.
Okay, what's the first one? Early fusion.
Yeah, early fusion. With this, the modalities are combined right at the very beginning of the pipeline. Often it's as simple as just concatenating their feature vectors before much processing happens. This allows for very deep, low-level interactions right from the start. But the downside is it can be brittle if there are data discrepancies, and it might even lose some modality-specific information because everything gets sort of mushed together too early. It's probably best for really tightly coupled data, like maybe text, and its metadata for sentiment analysis, where the info is inherently intertwined.
Okay. And then late fusion, which sounds like basically the opposite strategy.
Pretty much. Late fusion takes the opposite approach. Each modality is processed independently by its own model, generating separate predictions or features. Then these individual outputs are combined only at the very end, maybe through averaging or voting or some other mechanism. This approach is highly modular, it's robust, especially if one data stream is missing or unreliable. Makes sense, right?
Yeah, definitely.
But it misses out on those nuanced, fine-grained interactions between the modalities because the fusion happens too late in the game. Much of the specific context might have been lost by then. Think about analyzing medical scans separately from patient records and only combining the final diagnoses at the end. You might miss subtle correlations.
So if early fusion is potentially too early and late fusion is maybe too late, I'm guessing there's a Goldilocks zone in the middle.
Indeed there is. That's hybrid or intermediate fusion, which is really the dominant modern paradigm. This strategy integrates information at multiple stages throughout the model's architecture, often leveraging those sophisticated cross-attention layers we talked about. It tries to balance specialized processing within each modality with deep cross-modal interactions at various points. Generally, this achieves the highest performance for complex tasks, like, say, visual question answering. Though the trade-off is, it does increase the architectural complexity quite a bit. It's like having multiple conversations between the senses all the way through the thinking process.
And it sounds like choosing that fusion strategy isn't just an isolated decision at the end. it actually impacts everything else, going backwards.
Not at all isolated. The choice of fusion strategy creates constraints that ripple backward, influencing the required approach to representation and alignment. For instance, if you choose early fusion, you're implicitly committing to a joint representation scheme right from the start. This interdependency is a primary source of both complexity and, frankly, innovation in multimodal system design. These three pillars are always working in concert.
Fascinating. So, okay, what does this all mean for the actual AI models we're seeing pop up today? How have these foundational ideas played out in the real world, moving from theory to, well, some pretty revolutionary applications?
Yeah, we can trace a really fascinating evolutionary path through some seminal models, thinking about things like CLIP, Flamingo, and most recently, GPT-4o. Each represents a distinct philosophy for tackling these challenges and really pushing the boundaries of what multimodal AI can actually do.
All right, let's start with CLIP, contrastive language image pre-training. What made that such a watershed moment? It feels like everyone was talking about it.
CLIP was absolutely revolutionary, mainly because of its approach to learning this shared understanding between images and text. It uses what's called a dual encoder architecture, separate powerful encoders for images and text. But the real innovation is how they're trained. It used this massive data set, 400 million image-text pairs scraped from the internet, and is optimized using a contrastive loss function. Essentially, the model learns to maximize the similarity score between correct image-text pairs like an image of a dog and the text a photo of a dog, and minimize the score for incorrect ones. This forces the model to learn that shared embedding space where similar concepts, regardless of modality, end up close together.
And its key capability, the zero-shot learning thing, that sounds incredibly powerful. Does that really mean it can classify something it's never, ever been explicitly trained on before?
Precisely. That's the magic. CLIP can classify images into arbitrary new categories without any additional training data for those specific categories. You just turn classification into a similarity problem. So to classify an image, you feed it into the model along with a set of text prompts like a photo of a dog, a photo of a cat, a photo of a bird, etc. The model then predicts the class whose text embedding has the highest similarity score with the image embedding. It's classifying based on conceptual understanding across modalities, not just memorized labels.
Wow, that's certainly a fundamental shift from how we used to think about image classification. Does this zero-shot capability mean we might eventually need far less labeled data for new tasks across the board? What came next after CLIP?
That's exactly one of the major implications, yeah. Reducing the reliance on massive labeled datasets. The next really significant step, I'd say, was DeepMind's Flamingo. It introduced a different architectural philosophy, the bridged frozen models approach. Instead of training one giant multimodal model from scratch, Flamingo leverages powerful pre-existing and, importantly, frozen unimodal models. Think a state-of-the-art vision encoder and a large language model. And it connects them with much smaller, learnable glue components.
Glue components, that sounds interesting. So it's not retraining the whole massive thing each time, just the connections.
Exactly. The core models, the big vision and language ones, are kept frozen. This preserves all their vast pre-trained knowledge. The glue consists of components like a perceiver resampler, which efficiently distills a large number of visual features down into a small fixed number of visual tokens. And then these things called gated cross-attention dense layers, which are strategically inserted into the frozen language model. These layers allow the language model to basically look at and condition its text generation on those visual tokens, but without needing to retrain the entire gigantic language model. It's much more efficient.
Okay, so beyond just being a clever architecture, what unique capability did Flamingo really unlock for multimodal AI? What was its superpower?
Its superpower is really impressive few-shotting context learning, specifically for vision language tasks. Flamingo can be prompted with just a handful, maybe 4 or 5 interleave image text examples demonstrating a task, like visual question answering. And then it can perform that task on new inputs without any further training or gradient updates. It adapts to new tasks just from seeing a few examples, which makes it incredibly agile for new applications.
Okay, from CLIP's zero-shot to Flamingo's few-shot. Then we arrive at GPT-4o, with the O standing for omni. This feels like a really significant paradigm shift, not just another step.
It absolutely is. GPT-4 represents a truly natively omni-modal design. Instead of separate models or clever bridging, it's conceived as a single, end-to-end trained transformer. And this single network processes and generates any combination of text, audio, and image inputs and outputs. It all happens within the same neural network. All the inputs are tokenized into some common representational format and processed jointly right from the very beginning.
Wow. So it's not a committee of separate models working together. It's like one unified brain that perceives and produces everything. That's a huge leap.
That's the core idea, yes. And this unified architecture unlocks some incredible capabilities. First off, extremely low latency. Think about previous voice assistants. They usually had this cumbersome pipeline. Speech goes to text, text goes to a large language model, the LLM generates text, then text goes back to speech.
Right, that delay can feel really unnatural.
Exactly. That chain could take seconds, totally breaking the conversational flow. GPT-4o, because it's end-to-end, can respond to audio inputs in as little as 232 milliseconds. That's comparable to human conversational response times. It's a total game changer for natural human-AI interaction.
I remember trying to get my old voice assistant to understand me over background noise. Forget it. So the idea that GPT-4 can filter that out and pick up emotional tone from raw audio, that's really something else.
Indeed. It also offers dramatically richer contextual understanding. When audio is just converted to text first, you lose all that crucial information, tone of voice, emotion, laughter, background noises. GPT-4o, by processing the raw audio directly, perceives these nuances. This allows it to generate responses with varying emotions. It can laugh, it can even sing, apparently. And finally, you get seamless modality interplay. It can fluidly handle real-time interactions. Imagine it watching a live video feed, listening to your spoken questions about what it's seeing, and providing a spoken answer, all in a continuous conversation. It can even do things like real-time translation between two speakers talking different languages, maintaining the context and flow. So the trajectory here seems pretty clear then. We've gone from designing clever ways to integrate separate models towards these unified tokenization schemes and end-to-end training for single, powerful omni-modal systems. Yes, fundamentally, the core problem is shifting from clever model integration to foundational data integration. It's about designing systems where all data types are inherently understood and processed together from the ground up, ideally within a single architecture.
This sounds amazing, but practically speaking, what about real-world applications? Can we actually build something useful with this right now, or is it still mostly research?
Oh, absolutely, we can build things. A quintessential example that really brings all three pillars, representation, alignment, and fusion, together in a tangible way is visual question answering, or VQA. That's where you give an AI an image and ask it a question about the image in natural language, and you accept a natural language answer back.
So like showing it a picture of a busy street and asking, what color is the bus? That requires it to both see the bus and understand the question about its color.
Precisely. It inherently requires representation of both the image and the text question. It needs alignment to connect specific parts of the image, like the bus, with concepts in the question, color, bus. And then it needs fusion to combine that visual and linguistic information to generate the correct answer, like the bus is red. It's a perfect showcase for how vision and language understanding have to be integrated to solve a complex problem that neither modality could possibly solve alone. And interestingly, for building a production-grade VQA system today, the engineering effort actually shifts quite significantly.
Shifts how? What becomes the main focus for engineers if they're not designing the core model?
Well, modern multimodal development often centers more on the skillful composition and fine-tuning of powerful existing open-source components, rather than building entirely novel models from scratch every time. For example, you could leverage a robust pre-trained model like, say, BLAP from a library like Hugging Face. You'd fine-tune it on your specific VQA dataset to tailor it, and then you'd focus on deploying it as a web service, perhaps using tools like Flask for the API endpoint and containerizing it with Docker for portability and scalability. So the primary engineering effort often moves away from novel model architecture design and towards things like robust data pipelining, ensuring data quality, efficient deployment, monitoring, and lifecycle management.
Okay, so if we're building and deploying these increasingly complex systems with maybe multiple models or components working together, how do we actually run them reliably and keep them healthy in the real world? This sounds like MLOps, but on steroids.
You're spot on. Operationalizing multimodal AI definitely extends traditional MLOps practices because of these unique complexities. The unit of management is no longer just a single model. It becomes what we often call a complex, interdependent system graph of components. Think about it. A silent failure, or even just subtle data drift in one modality's processing pipeline could subtly, or sometimes even catastrophically, degrade the entire system's performance, and it might be hard to pinpoint why.
So how do we even version these complicated systems? It can't just be about tracking the code anymore, right? You've got models, data.
Definitely not just code. Beyond source code, these large data artifacts,
Yeah.
the datasets themselves, the model checkpoints, which can be huge, must be meticulously versioned. So you'd use Git for your code, naturally. But for managing those massive data files, tools like DVC, data version control, become pretty essential. They let you track changes to your datasets just like you track code changes, ensuring reproducibility. We also tend to use semantic versioning for the models themselves. So a major version change might signal a breaking change, like swapping out the core image encoder. A minor change could be for new functionality or a performance boost. And a BAS-ECH is typically for bug fixes. And crucially, comprehensive experiment tracking is absolutely vital. Meticulously logging every single training run, we're talking the code hash, the specific data versions used, all the hyperparameters, the resulting metrics, the URIs pointing to the saved models. This ensures reproducibility. Tools like MLflow or weights and biases are indispensable here.
Right. And the performance monitoring must be way more complicated too. You're not just looking at one input stream or one simple output accuracy.
Well, yeah. What's fascinating here is that monitoring is significantly more complex because of those intricate interactions between modalities. You absolutely need to track data drift and data quality independently for each modality. For instance, are there sudden changes in average image brightness in your visual stream? Or is there a significant shift in the vocabulary being used in your text input? But a unique and really critical challenge for multimodal systems is detecting what we call cross-modal inconsistency.
Cross-modal inconsistency. What exactly do you mean by that? Like the senses disagreeing?
Exactly. Imagine an insurance claim scenario.
Mm-hmm.
A user submits an audio recording describing just some minor damage, a scratch really, to their car, but then the photos they upload clearly show the vehicle is, totaled.
Ah, okay. That's a big discrepancy.
That's a major conflicting signal between the audio and visual modalities. The monitoring system needs to be smart enough to immediately flag such inconsistencies. This isn't just about detecting a bug in the AI model itself. It's about the AI essentially saying, hey, human, something doesn't add up here in the real-world data I'm receiving. What I'm seeing and what I'm hearing contradict each other.
Wow, an AI flagging existential doubt about reality. That's quite something.
It highlights the power and the challenge. And of course, alongside this, you still track all the traditional operational metrics, latency, throughput, error rates, system resource usage, and so on.
And given how fast this field moves, how do we keep these complex deployed systems up to date and improving over time? It can't be static.
No, definitely not. Automated retraining and fine-tuning pipelines are absolutely essential. We rely heavily on CI/CD pipelines, continuous integration and continuous deployment, often orchestrated by tools like Kubeflow pipelines or Apache Airflow. These pipelines automate the entire ML workflow: data ingestion, validation, pre-processing, model fine-tuning or retraining, rigorous evaluation against benchmarks, and then controlled deployment into production. These retraining runs can be triggered automatically based on various factors, maybe on a regular schedule, or perhaps when monitoring detects significant performance degradation, or maybe when substantial data drift is flagged in one of the modalities. And finally, closing the loop with human-in-the-loop feedback is incredibly crucial for continuous improvement. Capturing corrections from human reviewers on the AI's incorrect predictions allows us to create a virtuous feedback cycle, constantly refining the AI's understanding and performance over time.
This all paints a picture of a really dynamic and, frankly, exciting future. It definitely raises the question, what is next? Where is all this heading for AI that can perceive and reason across all these different types of information? You mentioned embodied AI earlier.
Yes, exactly. The long-term vision for many in the field is moving towards embodied AI systems that don't just passively perceive and reason, but can actively interact with and manipulate the world around them, whether physical or digital. And one key trend enabling this push is the continuous effort to achieve powerful performance while using less data. The bottleneck of needing vast, meticulously labeled training data is still huge, especially for complex multimodal systems. So overcoming this is critical.
So we're talking about things like zero-shot learning and few-shot learning becoming even more central and effective.
Precisely. Zero-shot learning, or ZSL, allows models to perform tasks on categories they've never explicitly seen during training, just by leveraging that shared semantic space we talked about with CLIP, classifying a new object based purely on a text description, for example. And few-shot learning, or FSL, enables models to learn new tasks rapidly from just a handful of examples, often through that kind of in-context learning demonstrated by Flamingo. These approaches significantly mitigate the expensive data labeling bottleneck, making AI much more agile, adaptable, and scalable to new domains and tasks.
Okay, and then there's this idea of the rise of agentic AI. This sounds like AI moving beyond being just passive tools we query towards something far more proactive and autonomous.
That's the fundamental shift, yes. We're moving from reactive models that just respond to prompts towards proactive autonomous agents, agents that can perceive their environment through multimodality, reason about complex goals, formulate plans, and then execute sequences of actions to achieve those goals. Multimodality provides the necessary, rich sensory input for these agents to truly understand their context. Vision might be used for navigating graphical user interfaces or physical spaces, audio for understanding spoken commands or ambient sounds, and language for complex reasoning, planning, and interaction. It's the senses that make these agents truly aware and capable.
So the multimodal capabilities are essentially providing the critical sensory foundation for these agents to be genuinely intelligent and interactive in complex environments.
Yes, exactly. And this directly leads to the emerging class of models, sometimes called Vision Language Action or VLA models. These models are trained not just to describe what they see or hear, but specifically to map their multimodal perceptions directly to sequences of executable actions. This moves AI from being purely about information processing towards active manipulation, whether that's controlling software, navigating websites, or eventually controlling robots in the physical world. This really paves the way for general-purpose robotics and highly capable AI assistants.
And thinking about the output side, what about the future of generation? We're seeing amazing text and image generation, but what's next beyond that?
Yeah, the field is rapidly pushing into much more advanced cross-modal generation. We're already seeing impressive progress in text-to-video models like OpenAI's Sora or Google's Video Poet, which can create high-fidelity, temporally coherent video clips from textual descriptions. There's also work on generating video directly from audio narratives or generating realistic 3D assets from text prompts or 2D images. The boundaries are really blurring.
So the ultimate goal then is maybe a single, truly unified generative architecture, one model to rule them all, so to speak.
That seems to be the long-term dream for many, yes. A single, unified foundation model that can fluidly generate content in any modality, conditioned on input from any other modality or combination of modalities. It's about treating all these different data types, images, text, audio, video, perhaps even things like motion or tactile signals, eventually as interchangeable tokens within a shared generative process. This convergence of data-efficient learning like ZSL and FSL, agentic reasoning and planning, and advanced cross-modal generation really points towards a future where AI systems are much more active participants in our world. They'll be capable of understanding complex multimodal instructions and executing sophisticated generative and interactive actions in response.
Wow. Okay, from those foundational concepts, representation, alignment, fusion, through the evolution of really key models like CLIP, Flamingo, and the truly omni-modal GPT-4o, and even digging into the practical weeds of MLOps for these incredibly complex systems, we've covered a huge amount of ground today. It's crystal clear that multimodal AI isn't just some niche research area anymore. It feels like it's becoming central to the future of how AI perceives, reasons about, and ultimately interacts with our multifaceted world.
Indeed. And it leaves us with a fascinating thought to ponder. If multimodal AI continues on this trajectory, really dissolving the lines between different data types, enabling AI to not just passively understand, but to actively act and create across any modality, how might that fundamentally reshape our daily interactions with technology? Could we be moving from seeing AI as mere tools to perceiving them as truly embodied, interactive partners in our digital and maybe even physical lives?